Let's master every stress from Le Chatelier's principle. We are going to look at change of concentration, change of pressure, and a change of temperature. I have given you a very classic reaction, the Haber process. We have hydrogen gas react with nitrogen gas to form ammonia. We're going to predict, so this is a beautiful equilibrium, what happens to the equilibrium when we stress the system these 6 different ways. I'll tell you right now, if you can do this, you can do any Le Chatelier problem. This is masterful practice. So let's begin. Changing concentration. Now, if you need to go back to one of my former videos on me talking about the teeter-totter, please do that. This is practice just to make sure that you've mastered the concept. Okay, we are going to increase the amount of hydrogen. So let's add hydrogen. I'm at beautiful equilibrium. I add hydrogen. Think about the child that jumps on the teeter-totter. So this hydrogen, I have extra hydrogen. This goes out of balance. Too many reactants. Because there's more reactants, there's going to be more reactions. This rate speeds up. The rates are no longer equal. We're not in equilibrium. So this rate speeds up. What does it do? It shifts forward. So this reaction, and remember there are 3 ways that you can do this. This is going to shift forward. I could also say it could shift to the right, or I could say it's going to shift to products. Proceeding, I'm just going to do an arrow, okay? This is going to shift forward. Sorry, that might be kind of hard to read. I'll use a blue marker for our next one. Okay, now we're going to remove a product, remove the ammonia, and we do this often. It's called harvesting the product. So I'm at beautiful equilibrium. Let's remove some of that ammonia. If we remove that, think about the child jumping off of the little seesaw, the teeter-totter. This side gets light. It goes up like that. So I'm thinking whichever side's lower, that's the one that has more. Again, this reactant side has too many. It has more reactants than what we have at our equilibrium. And so more reactants, more collisions, this rate speeds up and it's going to shift forward. So this also will shift in the forward direction. Okay, let's change gears. We're going to go to pressure. Here's your big takeaway. Remember, if you increase pressure, it's going to go to the side with fewest gas moles. I remind students that if you increase pressure, you have more collisions on the side of the container. So it will shift to the side that has fewer gas moles to decrease the number of collisions, decrease that pressure. Now, the trick that professors love to use, instead of changing pressure, what do? They change volume. Well, you and I know Boyle's law. It's an inverse relationship between pressure and volume. If I increase volume, that means we decreased the pressure. Okay, and then I'm thinking through this. Sorry, you guys, I don't think you can see that one very good either. We decrease the pressure. Well, if I decrease pressure, that means that this is going to shift to the side with the most gas moles. I'm going to write that down so you have it. So shift to the most gas moles. Let's count gas moles. I have 1, 2, 3, 4. So 4 gas moles. Over here, I only have 2 gas moles. Which side has the most? It's the products. Oh, excuse me, it's the reactant side. So this is going to shift reverse because it has the most gas moles. Now let's switch it. We're going to decrease the volume. So if I decrease the volume of this container, it's going to increase the pressure, increase pressure. All right, increase pressure, it will shift to the side with the fewest gas moles. Fewest gas moles, 4, 2, 2. Is going to shift forward. And this is to the least gas moles. Okay, nice. Our last one, change of temperature. Remember for this, I have a hack. And if you need to, please go watch the video on the change of temperature. This hack, it always works, but know that it's a little bit of a, something that we made up as chemists to help us. It's not like a true representation. Okay, Negative delta H tells us that this is exothermic. The reaction releases energy. It's almost as if the energy is a product. So when you see that negative delta H, you think, oh, releases energy. Write the word heat on the product side. Likewise, if this was a positive delta H, positive enthalpy, endothermic, absorbing energy, you would write the word heat on the reactant side. Now, we pretend that the heat is a concentration. So as we change temperature, that's what we change, is this word right here, thinking, are we adding or taking away? You and I know when we change the temperature, it applies to the whole reaction. Remember, this is a hack, a trick that we use to figure it out. Okay, so let's put this in a warm water bath. We're going to increase the temperature. When I increase the temperature, okay, it was a beautiful equilibrium. I increase the temperature, it's like I'm adding all that energy just to the word heat. That gets heavy. I have too much energy, too much heat. So in this situation, what happens? I'm going to have more reactions for my products. The rate speeds up, so it shifts in the reverse direction. So this will go reverse. Now, let's take this and put it in a cold water bath. So we're an ice bath. Let's remove the heat, decrease the temperature. I'm at beautiful equilibrium. I have my word heat right there, and I'm going to remove the heat. Put this in the ice bath, pull the heat out. What happens to my teeter-totter? Goes like that. I don't have enough energy. I pulled some of that away. It's like the child jumping off the teeter-totter. So what's it going to do to go back into equilibrium? It will shift forward. It will shift forward. And you know, in my little example, whatever side is lower, that's the reaction that's going to go faster. The rate is going to go faster. The one that's higher, the rate goes slower, and it always shifts from that high to low to go back into equilibrium. Okay, great job. I'm so proud of you. If you need help or support, you have more questions on these, please go back and it's in the acid-base equilibrium section. You can watch the specific stresses and get more detail. If you have mastered this, you're perfect. You've got Le Chatelier's principle. Good work. Remember, please like and subscribe to Old School Chemistry, and I'll see you next time. Thank you. Bye.